Okay, let's talk about the law of refraction. Remember, the law of reflection says that the angle of incidence equals the angle of reflection. Refraction is when light is bent. When you go from a material, you go from between one substance and another substance. Now, there's an important property of optical materials, which is called the index of refraction. And basically, N, we use the symbol N, and it's the ratio of the speed of light in a vacuum to the speed of light in a substance. So because nothing can go faster than the speed of light in a vacuum, then C is always greater than 0, since V is going to be less than or equal to C. Therefore, this is always greater than or equal to 1. And for a vacuum, N is equal to 1. The index of refraction for air is very close to that. Now, as we talked about in previous discussion, there's this relationship between wavelength and frequency and the speed of light. So you take the frequency times the wavelength to get the speed of light. And in this case, we said that the frequency of oscillation doesn't change. What happens is the wavelengths get shorter. So you can kind of think of it as a wave phenomenon. You got waves that are coming in here. Think of waves coming in. So they have a certain distance apart, which is your wavelength. And what happens at the interface, let's say this is n equals 1, and this is n equals 1.2. What will happen is, as these waves reach this interface, they will be bent so that, I'm trying to make sure I get this right, so they actually go this way. So the wavelengths get less because if the speed of light goes down and you have the same frequency, the wavelength has to get close together. So if you did an arrow that was perpendicular to these waves, it would go like that, and then it would bend like that. So the waves that are in this new material are going to be like this, and they're going to be close together. But if you saw these peaks of the waves past a certain point, they'd still pass at the same frequency. Okay, so as a consequence of that, the index of refraction, which is the ratio of the speed of light in a vacuum to the speed of light in the medium, is just the ratio of these wavelengths. So you have O stands for the wave speed in a vacuum, and this is the wavelength in the material. And if you do a little bit of geometry, just use some right triangle geometry, you end up with what's called the law of refraction. And it says that if you have light going from one material with a index of refraction of n1, and it has an angle theta 1 between the line that's perpendicular to the surface and the ray, that's equal to n2 times the sine of theta 2. So let's just draw a picture of what we're talking about here. So we have some interface. We have a light ray coming in. Let's assume that N1 is 1.1 and N2 is 1.3. I purposely picked something other than a vacuum just to show you. If it came from air or from a vacuum, N1 would be equal to 1 or close to 1. So then we can draw this vertical line. It'll go through both of these right there. So theta 1 is this angle, and theta 2 is that angle. So let's just look at an example. Let's assume theta 1 is 30 degrees. What we'll see is that if n2 is greater than n1, then the sine of theta 2 has to be less than the sine of theta 1 because the equality still has to hold. So the angle is going to get smaller. So we know theta 2, since n2 is greater than n1, theta 2 has to be less than theta 1. And if it was the other way around, it would go the other direction. So let's solve for the sine of theta 2, because that's what we're trying to figure out. We know theta 1 is 30 degrees. So you get the sine of theta 2 is equal to the sine of theta 1 times n1 over n2. So you just plug in the sine of 30 degrees times n1, which is 1.1, divided by n2, which is 1.3. The sine of 30 degrees is a half. So we get 0.5 times 1.1 divided by 1.3, which is 0.423. Okay, so what we're looking for is theta 2, so we'll take the inverse sine of both sides. So you take the inverse sine of 0.423. So let's see here, inverse sine of the answer is 25 degrees. So in this case, theta 2 equals 25 degrees, which is less than theta 1. It's that simple. So if you go from air into any substance or from a vacuum into any substance, you're going to be bending. You're going to make theta 2 less than theta 1. Now if you're going the other direction, you know, you can go both directions. You always think going in one direction, but you know, let's say this is n equals 1.3 and this is air, n equals 1.0. You can still have light going in the other direction. So you go here, we draw a vertical line that's perpendicular to the surface at that point. And so instead of bending towards the perpendicular line, it's going to bend away. So in this case, this would be theta 1, this would be n1, this would be n2, this would be theta 2. Because n2 is less than n1, then it bends the other direction. If this was, say, 1.5, it would bend towards the line. This one's bending away from the line. And this kind of, you can think of things like you're in the water looking up at the water surface. What happens to the light? If you just change the airs around, you can see that it would bend. Coming this direction, it's going to bend downwards. Okay, now one thing we'll talk about this later, but if you have this situation where you're going from a high index of refraction to a lower index of refraction, this thing's going to bend, and at some point you actually will have the, let's just show you what happens. So let's say we do this, and then it bends away, so it'll go like that, and there'll be some angle here where it can't bend out, and it'll actually just bend inwards like that. It'll reflect inwards. Let me erase those lines so they don't confuse us. Okay, that's all we have to say about that, I think. Well, we could talk about the index of refractions of certain materials, and that is listed on page 738. So I'm just going to show a few things. So we have a vacuum. This is N, 1.0. Air, 1.000293. So you can say it's essentially equal to 1. Then you have liquid water. It has an index of refraction of 1.333. And then you have zircon. Its index is 1.923. And you have a diamond. which is 2.419. So the light bends considerably. You know, you've probably heard of cubic zirconium, which is a fake diamond. And if you look at just glass is about 1.66. So if you made a diamond, or not a diamond, but made the crystal out of glass, you would get 1.66. If you make it out of zircon, it's 1.9. If you make it a diamond, it's 2.4. This will be important later on relative to this internal reflection. The higher the index of refraction, the more likely you are going to have internal reflection of more of the light. So what happens is basically the light gets in there and then it bounces around and then it comes out and it sparkles. So that's the sparkling thing. Anyway, those are some examples. You can look at some more of them on page 738 in your book.